Okay, so once we understand the various types of thrust conditions due to nozzle expansion, optimal under expansion, over expansion, optimal expansion of the nozzle, then we have seen the effective exhaust velocity C, how we can relate it with the thrust force. So, which is related with ISP of the rocket. Again, the characteristic velocity, which is just an ideal velocity, which is considered to take experimental data from our the ballistic bomb testing or rocket test performance parameter, and which is independent of nozzle characteristics. And it is the related with the efficiency of the combustion process. And then another thing is the area ratio. That is another important parameter. So whenever we are designing our rocket, the rocket area ratio have important values. So which is exit area divided by throat area. That means we can go to our this thing. Let me go to, yeah, area ratio means this. So when we say area ratio, anyways, let's go. Okay, so it is the measure of gas expansion provided by an engine. Okay, so optimum area ratio provides an exit plane pressure equal to local ambient pressure. Look, this is the condition. So when the exit pressure equal to the local or ambient pressure, that we call optimum area ratio. For a sea level first stage engine, the optimum area ratio is selected near midpoint of the flight. So the optimum area ratio is selected near midpoint of the flight. So we select an optimum area ratio. Most of the time we take 10. Area ratio is equal to 10, means exit area, because our nozzle is like this. So in our nozzle design, it is like this. So we have throat area here, and we have exit area here. This is area exit, and this is area throat. So in most cases, we maybe select 10 as a command. And it depends on your design, so that this 10 is not just a fixer, but we can check our performance by 10 design. So for a spacecraft engine in upper stage, that is upper stage engine, what are these stages? We'll discuss on how to staging. Okay, in most cases, rockets are designed with staging. Almost all current rockets are having multiple stages on it, either parallel or tandem or series staging is there. So in upper stage engine, the optimum area ratio is infinite. Look, sometimes infinite optimum area ratio also comes. The largest area ratio allowed by the space and the weight is used. An engine with area ratio less than optimum is referred to as under expanded. This means P exit minus PA PA less than 0 ከሆነ ምንድን ነው የምንለው? አንደር ኤክስፓንድድ ነው የምንለው። ይሄ ኦፕቲመም የምንለው ደግሞ PE is equals to PA ሲሆን ነው። That implies PE minus PA is equals to 0. So this is under expanded condition. So the exhaust in an under expanded nozzle can separate from the wall. This is called turbulence condition. In the exit wall of the nozzle, there will be some backflow of the turbulent gas which come out will be start circulating on that. There is one technical word for this. I will remember it later, but we use that. So this causing circulation and substantial loss of energy will happen. So that this is.
I think it is vortex. It's vortex, I think. Vortex ነው መሰለኝ። vortex.
Exactly. That it causes vortex at the exit of the nozzle. Vortex ነው የሚባለው። Good, thank you for your. So that causes the loss in the overall efficiency of the thing. So ያን ለማለት ነው። እንትን separation, flow separation ያደርጋል። That is called vortex. Okay, so another technical term is total impulse. It is the product of force times time. It is just thrust times time. So this is called, and the unit is Newton second. And this is what we call total impulse, which we use most of the time in our most discussions. So force is m dot VE. Therefore, by considering only the momentum term, our thrust is m dot VE. This is momentum thrust. If one consider the thrust as being almost, so what it is, how it is related with our rocket equation. This is actually our rocket equation. So total ISP is equals to IT over MP. So that ISP is equal to IT over MP G naught. So considering that, substituting it into our rocket equation, delta V or V final minus V initial of the rocket, which is equal to delta V, which is equal to IT over MP ln of initial mass over final mass. So which someone can express a matter of initial mass is mass of rocket plus mass of propellant. Okay, so over mass of rocket. Mass of rocket, when I say mass of rocket, the mass without considering any fuel or any propellant on it, just a skeleton, including the payload, other things. Okay, so this is the rocket equation, modified rocket equation on this aspect. And then using some Taylor series expansion for this, considering the mass propellant of propellant mass flow rate at this mass of rocket over mass of propellant as very less, means MP is very less than M of the fuel, the final. Then what we have, this equation gives this equation. You can take this as one of the equations, so that ln 1 is just okay, ln 1 plus ln of MEP over MR, that finally gives us IT over MEP is here, the first term, and this ln component gives us MEP over MR, so that you can remove MEP by MEP. You have left IT. IT means total impulse over mass of rocket. So this is the rocket equation again. So why we are using total impulse? That is what impulse in በቀጥታ ከግራፍ ላይ ማግኘት እንችላለን። ምን በማድረግ for example, we have this typical thrust time curve. So as I told you, thrust time curve depends on propellant types. Again, propellant shape, propellant internal slots like star shape, some kind of fully cylindrical or what, and is it progressive, regressive, or neutral burning? So propellant burning is one of the parameters for the thrust time curve. So this is the thrust time curve. From this we can easily get the total impulse. It is the summation of force times delta T. If you come to here, look, we have T naught here initially, maybe it is 0 or some T naught. Again, we have T1, T2, and T3 like this. Just taking this part of the, so the thrust for this point, F1, yeah, F1 here, the thrust for this part, F2. So simply averaging the area under the force time curve, what we can get, or integrating it, what we can get, that is total impulse. So this is simple mathematical calculation. You can F naught plus F1 over 2, F naught plus F1 over 2 times T1 minus T2. This is delta T, okay? Again here, F1 plus F2, F1 plus F2 over 2, T2 minus T1, T2 minus T1, plus continue just for others also. By doing that, finally we can get. So this T1 minus T2, just discretizing time in very equal points, we call it as delta T, or some change in time. So just put it. So finally what we can get in the rearrange, final and the initial thrust F naught and F final are 0, because it starts from here. It is and it ends at this point, so that F final and F naught are 0. So using simple Taylor expansion of the mathematical approach, what we can get, F1 plus F2 plus F3, summation of all forces times delta T. That is the method we can find total impulse from thrust time curve. Thrust time curve ተሰጥቷችሁ total impulse ፈልጉ ብትባሉ በእንደዚህ ማግኘት ትችላላችሁ። ወይም ደግሞ it is just integral of f dt. This means also summation ነው። ይሄ ማለት ምንድነው? Summation of fi times delta T. So this is the way how we can easily find. And another important term is specific impulse, which represents thrust per unit propellant weight flow rate. The specific impulse is equals to thrust over weight flow rate, or it is velocity, effective exit velocity over the G naught. So this is the specific impulse. How we can get the specific impulse? So this is the mathematical approach. We can easily get specific impulse, which is integral of this is just total impulse. IT. This represents IT. And this is impulse. This represents the force, IT. So G naught M mass flow rate dt. From this we can get which gives us G naught M. M dot T is M. M dot T M no. M here እንትን ብንል ምንድነው M dot ማለት mass per unit time አይደለ? M dot times ስንል ማስ ይቀራል ማለት ነው። ስለዚህ እዚህ ጋር የምናገኘው ያንን ነው። Or somebody can write it IT here, IT over G naught M dot T, because from this we can get some T. So M dot T means it is simply M. So that is the mass of propellant. So this is called ISP. የተለያዩ ሬሽዮች አሉ ከዚህ በኋላ የምናያቸው። So mass ratio, what is the mass ratio? So that is just a measure of efficiency of rocket actually. It describes how much more massive the vehicle is with the propellant than without. That means the ratio of rockets wet mass. That means wet mass means vehicle plus contents plus propellants. እዚህ ጋር ሶስት ነገር ተመልከቱ። vehicle አለ, that is the rocket itself. Contents are the structural mass, the payloads, the communication systems, navigation systems. እነዛ content ሲሆን then propellant also. So that is called wet mass. Wet mass ብዙ ጊዜ ስታገኙ overall content ነው። Two, it is dry mass. Now when we come to dry mass, it is vehicle mass plus contents. This is without any propellant. Look, this one is dry mass is the vehicle without propellant. Once all the propellants are consumed, or else there is no propellant loaded into the vehicle, then it is called dry mass. And if there is propellant on it, it is called wet mass. So when we come to the mass ratio, it is total vehicle or of the particular vehicle stage of the propulsion system. So how we can define mass of fuel over mass of oxidizer. So mass ratio is equal to mass of fuel. This MF is equals to fuel mass. Or እዚህ ጋር ምንድነው fuel and oxidizer መውሰድ እንችላለን። No, this case no. አይደለ ያኛው stochastic ratio ወይም ደግሞ በኋላ mixture ratio ነው። ይቅርታ
final mass over
mass of final mass to initial mass ማለት ነው። Final mass ማለት without propellant. Mass with no propellant. Means once all the propellants are consumed, and this is mass with propellant ማለት ነው። So this equation implies they're either in single stage or multi-stage vehicles. Still stage ስናወራ በኋላ የምናወራው ስለሆነ ችግር የለም ነው። The overall mass ratio is the product of individual vehicle stage mass ratio. So there are booster stage at the very initial, that is heavy stage. And then there are sustainer stage. Means once the booster stage is dropped from the staging, then it will continue to the sustainer stage and the third stage, fourth stage. So all stages have its own propellant. So it is for overall mass ratio in the product of individual vehicle stage mass ratio. Okay. So the final vehicle mass MF has two induced components such as guidance system. Look, the vehicle system alone or dry mass of the vehicle is, it contains the rocket structure plus guidance device plus navigation gears or navigation device plus the payload which instrumentations and other things which we put into space. Okay, this includes maybe scientific instruments, maybe military, some warheads in case of missile. It also contains flight control systems or device. It also contains communication device. Okay, communication device. The power supply systems. Okay, continuous power supply systems are also there. The tanks, the structural tanks, the residual propellants, maybe some residual small propellant may left which not useful. Again, along with all the propulsion hardware, the propulsion systems also all. So these are called mass of the final mass. That the final mass is mass without propellant only. Okay. Now another term is propellant mass ratio. Propellant mass ratio is the ratio of mass of propellant over mass initial mass. Just only mass of propellant. So from that, we can mass naught is equal to mass of propellant mass final. So mass final means the dry mass of the structure. So this is wet mass. This is just propellant mass. And propellant mass is equals to initial mass minus final mass. So we can put it like this. This MP is equal to initial mass minus final mass. So just this means 1 minus MFM naught. Okay. So this symbol represents propellant mass ratio. So just you can take a simple example like the complete space shuttle system has fueled weight at liftoff is 1,708,500 kilogram, and the dry weight at liftoff is 342,100 kg. So what is the propellant mass fraction? So you can easily calculate. It is from this formula. You can use any of the formula, then you can get this answer. It is 0.7998 is the propellant mass fraction. Impulse to weight ratio. That is also another important parameter, IT over W naught. So the impulse to weight ratio of a complete propulsion system is defined as the total impulse. The total impulse IT. This is IT. Total impulse divided by the initial or propellant loaded vehicle. This when we say W naught, initial or propellant loaded vehicle at sea level weight. Okay. W naught. So that means IT over W naught, which is equal to W naught is mass of propellant plus mass of final mass plus propellant mass. Okay, so which gives us ISP over MP plus 1. So this is a general representation because ISP is equal to IT over MP G naught. Thrust to weight ratio. Again, this is there in the George P. Sotan book. You can find this notes. So the thrust to weight ratio, or we call it as yeah, it is this rocket propelled vehicle. It is an indicator of the acceleration expression. Okay, this is just acceleration. Okay, so our acceleration is just gravitational acceleration G naught. It is not G but G naught. G is some variable gravity. So rockets and rocket-propelled vehicle operate in wide range of gravitational environment, including the weightlessness environment. So this ratio has an effect, so that its values are drawn in table 2.1 in George P. Sultan. You can check it from page 30 of George P. Sultan. This is some charts which helps us to identify the ISP and the thrust to weight ratio in the for different type of propulsion systems. For example, what is the value of ISP for the liquid and solid chemical propulsion system, in monopropellant system, in cold gas system, in resistor-jet or this iron propulsion systems, means electric propulsion, I mean, and solar heated H2, nuclear fusion, arc jet. So these propulsion systems we discussed in last class, so you can understand them, how we can get ISP, how we can get thrust to weight ratio. So here it is thrust to weight ratio, and here it is ISP. So you can get it from Wikipedia. I got so actually it is there on the book of George P. Sultan, but this one is adopted from Wikipedia. Another thrust coefficient. So thrust coefficient is also another parameter that is it is a very important parameter in the design of nozzle, because it contains the nozzle parameters like combustion chamber pressure. It contains the throat area. It contains coefficient of thrust. Okay, so it contains the thrust itself. So thrust coefficient, thrust is equal to PC80 CF. So from this equation we can get thrust coefficient is equal to thrust over PC80. Okay, so and there are some two related parameters. C, specific velocity or characteristic velocity is equal to CF over C star. Okay, so thrust coefficient over C star gives us the characteristic velocity C. Again, ISP is equals to the thrust coefficient F CF times C star over G naught. So these formulas are very important in the nozzle design. Now another parameter is the mixture ratio. So mixture ratio is the ratio of oxidizer weight flow rate to fuel weight flow rate. This is very important in the design of the consumption of fuel and the oxidizer, or in the mixing of the liquid oxygen with liquid hydrogen. So how we can get an optimum ratio. So for example, the mixture ratio of a specific shuttle main engine have 6:1, means it is directly 6 parts of oxidizer, that may be liquid oxygen, which is mixed to 1 part of fuel, that is, for example, liquid hydrogen, LH2. So the mixture ratio is given, MR is equals to W dot naught over W dot F. So this is the mixture ratio. So we can get the mixture ratio and ISP from this. This is ISP, and towards to here we can see mixture ratio. So this also there in George P. Sultan book. Volumetric mixture ratio, which is just an extension of the mixture ratio. So it is mixture ratio times density of fuel over density of oxidizer. So this is called volumetric mixture ratio.
Sorry, teacher, doctor. On mixture ratio graph.
Can you repeat it once?
On mixture ratio graph.
Uh-huh.
Please come one page back.
ምን አልከኝ?
ሚክስቸር ራሽዮ ግራፍ ላይ ግራፍ
ኦኬ ያ
እዚህ ጋር እሱ ላይ ነው። ይሄ የስፔሲፊክ ኢምፐልስ ኢንክሪዝ እያደረገ በሄደ ቁጥር ሚክስቸር ራሽዮ ኢንክሪዝ ያደርጋል፣ ግን ከሆነ ፖይንት በኋላ ግራፉ ዲክሪዝ እያደረገ
exactly. So there is some optimum maximum ISP can be obtained at some point here. This point indicates the maximum ISP point. So that is the point where we need it. We need some propellant which gives us the maximum value of ISP. ISP maximum ነው የምንፈልገው። ያን የሚሰጠን ሚክስቸር ሬሽዮ ነው optimum mixture ratio የምንለው. So that our mixture ratio, for example, in this time, it is 2.7, I think. Just simple approximation. 2.7 is an appropriate mixture ratio to get good ISP. But at, for example, 300 ISP, we can get some value here. So some value here. And if I continue to this point, we can get also some value here. So ሁለት አይነት ቫልዩዎች እናገኛለን እዚህ ሪጅን። ለምሳሌ ይሄን 300 ISP ብንመርጥ ሁለት ቫልዩ ነው የምናገኘው። አንደኛው እዚህ ጋር ነው፣ አንደኛው እዚህ ጋር። So this is kind of graph which we can select which mixture ratio gives us an appropriate or optimum value የምለውን የምንመርጥበት ነው። So in this graph, most appropriately, this point is the proper point. So mixture ratio of 2.6. That means the oxidizer is 2.7, and the fuel 1. That means 2.7 to 1 ratio.
Yeah.
So there are also sometimes we use some bulk density concept. So bulk density concept is also in use. So it is mixture ratio plus 1 over mixture ratio over density of oxidizer plus 1 over density of fuel. That is called bulk density. So the bulk density and the mixture ratio for various propellant combinations are here. So this is there in the your textbook, that one of the textbook which we are using. So on that you can get this table. And another thing, I think we have no time. We have no sufficient time. Fundamental forces in aircraft የምንላቸው like thrust, drag, lift, weight. በተለይ የኤርክራፍት እንትኑ ባክግራውንድ የሌላችሁ ሰዎች ሎድ ሬሽዮ ምንድን ነው? ትራስት ቱ ዌይት ሬሽዮ፣ another lift to drag ratio የሚሉ ነገሮች ምንድን ናቸው? እና anyways maybe this thing is going to close within less than 1 minute. 10 ደቂቃ አርፈን እንቀጥል። ሄሎ፣
ከኔ በኩል ይቻላል።
ኦኬ
10 ደቂቃ አረፍ በሉና ከዛ ተመልሰን እንገባለን።
እሺ
ኤግዛክትሊ 8 ላይ ግቡ ብቻ 8 ደቂቃ